So which one is higher?
Is it okay?
Engineering is higher. That's why we are getting higher in compression. And tension opposite. So compressive stress, engineering compressive stress will be higher than engineering tensile stress in case of. Because the error you are making, you are thinking in terms of the applied stress.
Yes.
Think in terms of error you are making. Actual area is A dash, but you are treating this as A. So which type of error you are making? You are getting higher value or you are getting lower value? Area you are taking lesser. Actual area is more. You are taking lesser area. So the stress you will get will be higher or lower. Not the stress in the specimen. Stress in your calculation. Stress in the specimen is same. Material will fail at a given stress. Okay. Material will fail at a given stress. That is true stress.
Yes.
What you are computing, that may have error. So in computation, you have taken lower area than the actual. Think of this when it is subjected to tension. In this case, what will happen? This is A dash. This is A. So sigma true will be P over A dash, and that has to be same. The true stress in compression and tension is same. This is the element.
Yes.
Okay. And what will be sigma engineering in this case? P by A. And in this case, this sigma engineering, because A is larger. Okay. P is same. So sigma by A is going to be lower than sigma. So here it is higher than true. True is same in both the cases. This is higher and this is lower. So in compression, you are going to get higher stress, and in tension you are going to get lower stress. Okay. Yes. Actually, the model which Mender has developed, in that model he considers cylinders. So it will depend on, see, any empirical formula, for what it will be valid, for what conditions it will be valid. The conditions which have been used while deriving that formula. So when Mender derived the formula, he used cylinder strength. So if you want to use cube strength, you can use, but there will be slight changes in the coefficient. There will not be drastic change, but some change in the coefficients will occur. If you want to use cube strength instead of cylinder strength, or you want to use the actual strength. That's why when he was asking that why we are not multiplying by 0.85 here, we will multiply by 0.85, but later, after taking the effect of confinement on cylinder strength. Because the Mander's formula which has been derived, the Mander's model, he has derived for cylinder. That's why we will first do everything in terms of cylinder strength. And then we will convert into the structural strength by multiplying it by another factor of 0.85.
And so the equation that you have given for FS is valid from strain hardening to exhibit or
No, only in the strain hardening. From epsilon SH to epsilon SH. In that region only. It will be. Yes.
But in case of increasing pulse,
In case of
increasing pulse,
increasing pulse, okay.
we can take this as a one half cycle, and otherwise we can do main solution and take this half cycle and this half cycle.
Right.
So which
We will not take half cycle, we will take full cycle. Because this is the full cycle.
this as a
Full cycle.
one half cycle.
This whole cycle is like this. So this will take as a cycle, full cycle with this epsilon. And number of half cycles will be 1, 2, 3, and if it is coming 4. Like that.
And how to decide this main solution?
It will be simply integrating the epsilon. So that is 1/2 sigma max minus sigma. Any other question? Yes.
Last time when you were teaching us about columns, you had said that we should cast column up to a certain height
should cast the joint.
No, no, no. I only said that the joint should be cast along with the column. But I have not said that you will cast the column up to the face and then you will cast the beam. So how you are going to do it? The issue was anchorage of beam reinforcement into column. So this beam reinforcement is to be taken into column for a length LD plus 10. Okay, so how you are going to cast it? Earlier, or if the beam and column are having same grade of concrete, then what you can do? You can cast up to this level and then the remaining part you can cast along with the beam. But if the beam and columns are of different grade, then what you have to do? First you have to cast your column up to this point, then you have to place the beam reinforcement, then you have to cast your column here, this portion of the column, with the same grade of concrete as the column, and then you will cast beam and slab. Okay?
Sir,
Yes.
if you are casting like this,
Huh.
then how can we say that casting is done monolithic?
Okay. What is meant by monolithic casting?
Monolithic casting means at one time we cast.
We should cast the whole concrete at one time.
And,
Can we cast the whole building at one time?
No, one building not one.
We can't. So what we do?
We go constructing one floor, then another.
So we always have to have construction joints. Whatever structure you are constructing, there will be always construction joint in the concrete. We can't construct the whole structure, whichever structure you are casting. We can't cast the whole structure together because that much shuttering, and if it is small, you can do it. If it is just a small column, perhaps you can do it. Otherwise, you can never do it. Whether it is shear wall, whether it is column or beam column, frame, whatever. So what should be done there? And when you are casting the next portion, what we call lift. So one lift and the next lift when you are casting, its bond with the original concrete is very important.
Yes.
Okay. Now when we have interface between old and new concrete, what are the forces being transferred here?
One is friction.
One is the compression, another is tension and bending and shear. Okay. So concrete we do not expect to take tension.
Yes.
Concrete we expect to take
Shear and
compression and shear. So in compression there is no problem. This concrete and this concrete, if it is compressing and if there is even a joint, weaker joint, it doesn't matter.
Yes.
Okay. For tension, what should be done? Tension is taken by steel. Steel anyhow is continuous here.
Yes.
So steel we have not provided that. Problem is shear. That concrete should provide good interlock for shear transfer. For that, two things are to be done. Suppose this is my original column which I have casted here, and above this I want to cast the next lift of the column.
Yes.
So what should be done here?
Shear.
For shear transfer?
Shear.
First of all, this surface should be rough. Okay, when we will cast the next lift, then it will follow exactly the same shape which we have done here. So it should not be made smooth. That is one thing. Secondly, we should provide a key here so that the new concrete can also take this shape and there is interlock. Okay. Third thing is how this friction is going to work. That will work against this applied force and the tensile force. Okay. So the steel which we are providing here, that is also important. So this steel which is here. So how much tensile force this steel can take? Only that much compressive force can be applied here. If there is no axial force, axial compression acting. Okay. So this steel, amount of this steel is also important. Okay. That's why if you recall design of shear walls, there we had a special check for vertical steel for construction joint. So at construction joint, you have to ensure that minimum steel is provided. So this steel acts in tension, and as a result, it applies reaction here, which gives rise to friction force. And when this is trying to bend, suppose this is trying to slide here. So this steel has to bend like this. So it will act what we call as dowel action. So steel has dowel action. Steel causes friction, or it causes normal force which results in friction at the interface. So this steel is also very important. That's why in column we have a minimum steel which is 0.8%. In shear wall, the minimum steel is of the order of 0.25%, but that is to be checked. If requirement here is more at the interface, we have to increase the steel.
So, due to that bending, one side will be compression, one side will be tension. Due to that compression, that dowel action we can get. But how to, due to tension, how it will create compression force on concrete?
It will not. So when at this interface, let me change the color. At this interface, let us say this is subject to moment like this. So what will happen?
Yes.
This face will try to deform like this. As a result, what will happen? This will be subject to tension.
Yes.
Okay, and this side will be subjected to compression. So there will be net compression in this portion, and there will be separation here.
Yes.
Okay, so this portion which has opened up, okay, this is subject to tension. We do not depend on concrete to transfer the tension.
Yes.
Okay, compressive force will be transferred here.
Yes.
Okay, and this compressive force will give resistance for shear. Okay. So resistance for shear will act only in this portion.
Yes.
That's why we will see it later. Even if a beam is safe, let us say in shear, but it cracks in flexion, after cracking it may fail in shear.
Yes.
So originally in intact position it is safe in shear, but once flexion starts, then it may open up. Okay, and when it opens up, the contact area which will be available only above neutral axis, this will be able to resist shear force. So that area will be, which is resisting the shear force, that area will reduce, and it is possible that our member fails now in shear. Okay, so three types of failures we have. One is bending, another is shear, and one is what we call flexure shear. What is flexure shear? That the failure starts in flexure, but finally it fails in shear. So these three types of failure we consider. When we will talk about SC41 and the modes given there, I will discuss this again. Okay. Interesting. You are asking good questions. What else? The basic calculation you can find in any book, but these questions perhaps will be difficult to get in book. So these questions are very important. So when you will start thinking, when you will be doing problem, keep your mind open, think about those things. Do not take anything granted. ऐसा तो होता है. Don't take it like this. Think about it. Why it happens like this? Okay. So you will have this type of questions, and then your understanding will be much better. Anything else? If not, let's move forward. We will talk about bending of beams. You have already done in your undergraduate first year itself. We will revise that. Suppose I have a cantilever subjected to a vertical load here. It is going to bend. I take a small element here, length dx. Consider it here. It is subjected to m from this side and m plus dm on the other side. The length is dx. Okay, and what happens? This bends. The bottom fiber will get compressed. The top fiber will extend. What I have drawn is not precise. Actually, there will be extension here and compression. Extension here and compression. And if you join this, okay, you will get an angle which we call d, which is change in the slope. Okay, and d theta by dx, what is that? That is curvature. Okay, and this is depth of the neutral axis. This distance we call r, the radius of curvature. From here we take the distance y. Okay, from the neutral axis we take y. In the lower side it may be positive and the upper side it may be, depending on the sign convention you are using. And then you have derived different expressions with this. You have derived one expression that m upon I is equal to f over y is equal to e over r. You remember? All of you have done this. Can you derive it now? Okay, it's available in all the books. Any book on strength of material you will get. This is there. Okay. If you are not able to do it now, do it at your room. Okay. You should be clear how this is done. Okay. I am not doing it in the class intentionally. Okay. So you should do it. Another expression we have obtained is m upon I is equal to phi. Okay. Or perhaps you remember better in this form. This d square y by dx square, this is phi, which is also equal to d theta by dx, and theta is dy by dx, and this phi is also equal to 1 upon r. So if you have to get curvature in an elastic beam, you know how to obtain it. Okay, it is m over ei, the bending moment at that section, divided by ei, or if you know the displacement, then d square y by dx square. That will give you the curvature. Or if you know the radius, then 1 upon r will give you the curvature. Okay, you have done it, but perhaps you have not emphasized that much on curvature. You were more interested in y and f. Sorry, not, yes, y is the displacement, so y and f, there is one problem. This y is coordinate, I have used it here also, so I have to change it. It will not be d square y by dx square, either I have to change this, because this y and this y are different. This y is the distance from the neutral axis, and this is deflection. So both can't be same. So I have made an error, I will change it. Let me call it u. Okay, so please change it by u everywhere. So du by dx. So u is the displacement and y is the distance. Okay? Both are different. Now from this equation you can also see that m upon I or m upon ei, okay, that is f over ey. You agree? So that is f over e is what? In linear system, epsilon, strain over y. Okay, so if this is the strain diagram, this is the neutral axis, it is epsilon t, in our case this is epsilon c, and y is this, and epsilon at any distance is this. So what is epsilon over y? Epsilon over y is this angle. So this angle is also phi. So curvature can also be obtained from the angle in the strain diagram. This we will use in our further discussion. So I wanted to bring you to this point. So curvature can also be written as epsilon c over xu. We have taken y as the distance, so I will call it y. What is y? The depth of the neutral axis. Okay? That is equal to epsilon t over d minus y, and that is also equal to epsilon c plus epsilon t divided by d. You agree? From that diagram. This is the angle. This is total is d, and this is y. So epsilon c divided by u, that is same as epsilon over y, because the strain diagram is linear. And we will see, even when the stress becomes nonlinear, we continue to assume that the strain variation is linear. Okay, and what is the basis of this assumption that the strain will remain linear?
Plane section remain plane.
Plane sections remaining plane after bending. Okay, so two plane sections which is rotating with the neutral axis. Okay, the difference between them, that will be varying linearly. So the strain will vary linearly if we assume that the plane sections remain plane and perpendicular to the neutral axis after bending. Okay. Now in which case this assumption may not be valid? We discussed that also. Those beams which are having large shear stress, large shear deformations, there it will not be valid. So for slender beams, this assumption is valid. For deep beams, okay, if L by D is less than 2, okay, then this will not be valid. What will be the shape? In that case, if the plane section is not plane, what is going to happen? It will be warped. So this plane section which remains plane here, it will have this shape. So the plane sections after bending, it will have this type of shape. So variation of strain is going to be like this. Okay. What assumption we make in Timoshenko beam theory? We talked about Euler beam theory and Timoshenko beam theory. So here, this section, which was earlier like this, will be now like this, if it is plane. But due to shear, it will warp. In Euler beam theory, we assume that the plane sections remain plane. Okay, so it is valid for cylinder members. In case of squat members or deep beams, which theory we use? Timoshenko beam theory. In Timoshenko beam theory, plane sections remain plane or not? Plane sections still remain plane, but those do not remain normal to the neutral axis. Okay, so it's not that there we are considering warped sections. We are still considering plane sections, but those plane sections are no more. There is additional deformation. Okay, but those plane sections do not remain perpendicular to the neutral axis. The angle with the neutral axis changes. Why we do this? If actual section is curved, warped, why we are assuming plane? To simplify our calculation. Simple. Okay. So all these assumptions we are making to simplify our calculation. Let's first talk about cylinder beams. Okay. So in cylinder beams, plane sections remain plane, and there we will be using these relationships that curvature is equal to epsilon c over yu, or epsilon c plus epsilon t over d, or epsilon t over d minus yu. In all the three cases, we will get the same results. Okay. Now, out of these three, which one you will like to use in your calculation? Three expressions you have. You can use all the three. Which one you will like to use?
Last.
Why?
Because when we are deciding cellular criteria, we are deciding first what strain is he will take, and from that we will calculate curvature. And
No, at any point, we will see. You know epsilon c as well as epsilon t.
Yes.
You can use any one.
Yes.
Okay, but you can see that yu will be small. Generally, our neutral axis will be close to the compression phase in case of RCC members. In case of steel members, it is different. But in case of RCC members, concrete area in compression is much larger. Tension is taken by steel alone, so it will be close to the compression phase. Neutral axis will be closer to the compression phase. So yu is going to be small. Okay, and if you are considering the first expression, you will make error. Okay, so either second or third. It is always better to use third expression, where you sum epsilon c and epsilon d and divide by the total time. Okay. So if I have, let's take example of that same cantilever beam subjected to a fine load here. It is subjected to bending like this. Let me take a section here. Okay, let us say the moment here is n, and due to that there will be displacement. Okay, I want to plot a relationship between moment and curvature. Cantilever, so reinforcement I will provide at the top. Okay, I want to plot moment versus curvature. How can I plot? If I plot the strain at this section at any instant, okay, this will be epsilon t, this will be epsilon c, and I can get not theta but phi curvature. So how can I get it? I will apply P. Initially the P will be small. Okay. Then I will gradually go on increasing P. When I go on increasing P, the moment will go on increasing, and as a result, phi will also go on increasing. The curvature will also go on increasing. Okay. We have to plot their variation. How we can do it? Just I will assume some value of, let us say, epsilon t. I assume some value of epsilon t. Then some depth of the neutral axis I have to find out. So this depth of the neutral axis, which I wrote as yu. Okay. So what I have to do? For this value of epsilon t, I can get the force in steel. How? From the stress strain curve. So I have to follow the stress strain curve of steel. Okay. I can calculate the stress multiplied by area depending on where that strain is. Initially I will take a strain much smaller. So if this is the stress strain curve of steel, so first I will take here this strain, epsilon 1, I can take the strain here, epsilon 2, I can take a strain here, and so on. So I can go on increasing the strain. At each increasing strain, I can calculate T. Then I can calculate the depth of the neutral axis by equating C equal to T. Okay. So I will get yu by doing C equal to T, and I will also get epsilon C for that condition. The strain in steel from depth of the neutral axis, I will draw a straight line and I can calculate epsilon c as nothing but epsilon t divided by d minus yu into y. That will give me epsilon c. So I know epsilon c, I know epsilon t. Epsilon t I have initially assumed. Okay, I can get c and t, then I can calculate moment. So I can calculate moment versus current. So let us say this is m1 and this is phi 1 for the first value of epsilon t I have assumed. Okay, I can assume now a higher value of epsilon t. I will get m2 versus phi for the second value of epsilon t. For each condition, I am assuming a value of epsilon t. I am calculating the neutral axis by equating C with t. Okay, equilibrium. Then I can calculate moment for the corresponding location and corresponding value of epsilon t. Okay, I can calculate curvature and I can plot this m versus phi curve. This m versus phi curve will look something like initially the slope will be larger. Then the slope will reduce. From where the slope will reduce? I will explain you that also. Okay. Then it will achieve a peak value and then it may reduce or it may go depending on the section, reinforcement and concrete and grade. It may go like this or it may continue almost at the same level. Okay. So you will get this type of curve. Now, in the previous case, we have written m over EI is equal to 5. Recall? Look at the page. We have written that now. M upon EI is 5. So what is M over 5? EI. So this slope is giving me EI. So slope of the moment curvature diagram is giving us EI. Okay. Now I told you that the slope is not same. What does that mean? EI will change. EI is changing. Okay. Why EI is changing? Section is same. So why EI is changing? What is changing? E. Why E is changing? It is concrete only. So why E will change? Cracking. It is changing because of cracking. So till cracking occurs, so this is actually the moment corresponding to cracking. So that is the strain at which cracking in concrete will occur. How you can calculate the strain at which cracking in concrete will occur?
Equal to tensile strength.
Tensile strength.
We will calculate cracking moment and equal to 0.72 reps.
You know cracking strength of the concrete divided by modulus of elasticity of concrete, because I told you that the slope near the origin remains same in concrete in compression and tension. So E remains same. Okay. So you have to simply calculate epsilon T is equal to FCR divided by EC. So till concrete has not cracked, the moment of inertia will be much larger. And when the cracking in the concrete occurs, okay, the moment of inertia changes. It will go on reducing depending on the amount of cracking. Okay, as the cracking increases, when I will increase epsilon T, the cracking is going to increase, and as a result, the effective EI is going to change. So this we can call EI effective. What is EI effective? The tangential stiffness at any point. Okay, or secant stiffness at any point. That will change. Now, what will happen in case of a steel section? Does the steel section crack? So what will happen there? Sorry? Yielding. But before yielding, what will happen to EI? Is the EI going to change there? EI will not change there. So what type of curve you are expecting for a steel section? For a steel section, the moment versus curvature diagram you are expecting is that it is linear, and this slope is equal to EI, that is E into BDQ by 12. It has to be like that. Okay, then yielding will occur, and after yielding it will also take this shape.
Sir,
Yes.
in steel after yielding, the modulus of elasticity is 0 because it is constant. Then why it is constant?
We will see that also. Because when the modulus of elasticity of steel becomes 0, okay, it becomes 0 in bending in the top fiber, but not in all the fibers. The fibers below, let us say this is our steel section, or we have taken rectangle, so let us take rectangular itself. Let us say this is steel section. Okay, here is the neutral axis. So this is epsilon T. Okay, so epsilon T, let us say here it has reached epsilon Y.
Yes.
So what will happen? The modulus of elasticity of this portion will become 0. But what about the portion below? It has still not yielded. When the whole section will have zero stiffness.
When all fiber.
When whole of the section, and what we call that? Plastic moment. So when the plastic moment is reached here, then it will be constant. But before that, first yielding, first fiber will yield somewhere here. Then successive fibers will go on yielding. And here, whole of the section, actually whole of the section never yields. For that we will require infinite curvature. Why we will require infinite curvature? Can you tell me now? The whole section has yielded. What does that mean? In that case, what will be the stress strain diagram? When the whole section has yielded. This is, let us say, neutral axis. Rectangular. Rectangular means what? This. So what is this angle then? What will be the curvature? Epsilon over y. So that will become infinite. Okay. So this situation can be achieved only at infinite. But we know that when it reaches very close to the neutral axis, then there is not significant increase in the moment. And that condition itself we call MP. But in reality, the whole section right up to the neutral axis can never yield, because that will require infinite curvature. The section has to bend like that, which is not possible. Okay. So we will continue from here. This moment versus curvature, this is an important topic here, and this will be there in our discussion for long time. Throughout this course, in fact, we will be talking about moment versus curvature relationship. Yes.
Sir, this moment curvature diagram, we are talking about along this length, means up to top and this floor, there will be some bending moment here,
Right,
some,
right.
from that bending moment we will calculate stress, then from strain, and from strain
We can get curvature.
we can get curvature, then why we are assuming first strain, that we can directly calculate now.
You can calculate from strain only. So either you can first assume, both ways you can do. Either you first assume M and then calculate epsilon T and epsilon C and go ahead. But when you are assuming M, you do not know whether that M is causing strain in steel below yield or above yield.
That we can estimate now.
You can always estimate, but you have to do more iterations. You can do that. So M versus phi, basically we have to plot M versus phi.
Yes.
You can go on assuming values of M and go on calculating value of phi.
Yes.
That way it can be done. Okay. But suppose you assume M here. First M itself you have assumed here. What you are going to get?
No sir, that we don't assume. We
Uh-huh.
have plot P, we will put out bending moment
So you
diagram.
will assume P. P is not known. So you will assume some value of P.
Yes.
You do not know what you are assuming. Whether it is here or here.
P we also know, we don't design course.
How? How you know? For you have to design your whole section first.
Before doing any other analysis, we should know the what
So
design.
you can do with M phi also. Only thing I am trying to say is that if you want to do by assuming value of M, you have to do more iterations. You have to first see that where that M is, whether it is here in the curve or here, and you have to go on assuming large number of M, and then you have to see what strain. Finally, you have to come to strain.
Yes.
So what I am suggesting is that you assume strain directly. Strain in steel, you assume directly, and then back calculate M from there. Rather than first assuming M and then calculating strain, assume strain and calculate M. Because you are not calculating phi corresponding to any M. You have to simply calculate so many of points here. So you have to calculate these points and then connect those. You will get M phi. If you are designing for a value of M, then of course you have to calculate epsilon corresponding to that value of M. But when I have to plot the whole curve, what I need? A number of points there. So those number of points I can generate either by assuming M, then calculating epsilon, and then calculating phi. Or alternatively, I can assume epsilon, then corresponding M and corresponding phi. So this is requiring less number of iterations. Any other doubt? Anyway, we will continue this discussion.
There we are using epsilon C concrete. So will we take it a fixed value that 0.002?
No, it is a variable. Depending on epsilon t, epsilon c depends on epsilon t, the assumed value of epsilon t. Okay, so this will go on varying. It won't be a fixed value. Fixed value will be either at yield, when it will achieve the value of 0.015, then you will say that concrete has yielded. When it will assume the value, when it will reach the value of 0.0035, okay, then you will say that the cover concrete has fallen. When it will reach the value of epsilon cu in the core, okay, then you will say that the concrete has got crushed. At that strain, the concrete will get crushed. Finally, the failure is going to occur because of the crushing of concrete only. Because steel has much more ductility as compared to concrete, even if the concrete is confined. Okay, so we will continue from